Good morning and welcome to today's webinar. Thank you very much for joining us today. So today's webinar is on Molcart, the GigaSearch component of Molcart. And this method allows you to search billions of chemicals space, and it's the only currently available method to be able to do substructure search in such large data sets. My name is Andrew Ori, and if you have any questions after the webinar, please feel free to email or call. Contact details are here. If you have any questions during the webinar, please can you use the chat option in the webinar panel, or you can raise your hand at the end and we can open your mic. I'm also joined by Eugene Rausch, who is our principal software developer, and he's the main developer of this Molcart GigaSearch. So today's webinar will be recorded, and if you want to watch it, you can watch it on YouTube, or if you can also follow MolSoft on Twitter and Facebook and LinkedIn. You also get the link to the recording. So just a brief introduction about MolSoft, if you're not familiar with our company. We're a San Diego-based company, and we have it was founded by Ruben Abergayan. Max Totroff and Eugene Rausch are the principal developers of the software at MolSoft. Main customer bases are pharmaceutical companies and biotech, as well as academic labs. And the main software that we make is called ICM Pro. It's a family of software. Inside ICM Pro, we have tools for bioinformatics, molecular graphics, cheminformatics, ligand docking, protein-protein docking, QSAR, and many other tools. And subsets of those tools can be taken out into different products. But today's product you can use with ICM Chemist or ICM Pro. And ICM stands for Internal Coordinate Mechanics, and the original papers describing our method are here. I can provide those if you're interested in reading more about the method. So with the registration, you also get an ICM license. You just need to complete the license agreement, and then you can go to our support site and download ICM Pro full package. And when you open it, you'll see a host ID, and then you just need to send it to me or to info@molsoft.com, and we will send you a license key to activate the software. It runs on Windows, Mac, and Linux. So what is the application of GigaSearch? So chemical databases nowadays are getting exponentially bigger. Therefore, the ability to be able to search them becomes very important. And currently, the only available method is MolSoft's GigaSearch for substructure searching. So we're talking about billions of chemicals. Some applications of this method include, for example, you can efficiently search many billions of chemicals. You can build target-specific libraries. You can use the method to find chemical homologs to query chemicals. You can also use it to identify new leads and direct your structure-activity relationship search. You can find real chemical derivatives of lead compounds. You can also use it for virtual screening of chemicals for similar substructure. And you can output your search to fully interactive chemical spreadsheets for further analysis. And everything you see today can be scripted for batch or high throughput search. So how can you use a Molcart GigaSearch? There's two different ways. You can use it as a web front end. So you can, for example, Enamine use it as a web front end for their real database, which we'll talk about in a bit. Or you can download ICM Chemist or ICM Pro, and you can search directly from inside the graphical user interface. So I'm going to pass it over to Eugene now, who will describe a bit about the method that he developed and the original substructured approaches and the new GigaSearch and how they're different. Thank you.
Thank you, Andy. Can you hear me?
Yes, we can.
All right, thank you. So yeah, a couple of technical notes on substructure searching. So traditional approach, which is currently used in many other software, consists of calculating fingerprints, pre-calculating fingerprints, storing them in the database, and then you can use them to quickly filter unmatched hits, and then only apply subtractive search to the rest. So this method used in different software and used in Molcart, and it works reasonably fast on database sizes for like around 10 million of compounds. And most of the searches will complete in 10-30 seconds. The same fingerprint column can be used for similarity distance. This is implemented in Molcart as a chemical cartridge, which is a specific set of functions you can use from SQL language directly. And so next slide, Andy, please. So for the larger databases, this method actually has some problems. Well, the main problem is the speed. So because the size of the database is so large, so just reading all the fingerprint pre-calculated fingerprints will take much longer time than you need for interactive search. So usually it's going to be like minutes or even more than minutes, depending on the type of the query you use. So we developed the method which allows you to avoid this huge data scan, and in addition to the standard fingerprint storage, we developed a new, more efficient way to store fingerprints. So that allows us to read just a small portion of the database and efficiently filter out most of the unmatched hits. So that dramatically reduced the speed of the search. So it's actually increase the speed of the search. It takes like mostly for seconds to get the first hits and minutes to complete it on the whole databases. So for usually you need only to read like 6-10 bits from entire fingerprints, which is usually more than around 2,000 bits. And after that, so when we reduce the space, we applied standard Molcart search on the rest. So rest usually it's around a few millions of compounds, which can be reasonably searched by Molcart. And so yeah, that's pretty much it for the technical details. Andy will continue to show you some demo and some other benchmarks and everything else. Thank you.
Okay. Thanks, Eugene. Yeah, so as we mentioned, you can also you can have the GigaSearch as a front end. So Enamine has this. So one of the applications for this is for billion chemical searches. So Enamine has this real database, which is probably the biggest chemical database available at the moment. It's over 1.2 billion chemicals. There's a database of enumerated structures which they can synthesize within approximately 3 weeks with a greater than 80% success rate to synthesize them. So the current release comprises over 1.2 billion molecules, and they have certain properties that all these molecules have that sort of fall into the Lipinski rules and Weber criteria. And so we worked with Enamine to embed Molcart GigaSearch into their website, and so that enables them people to efficiently substructure search their database. So let's have a quick demo. So if you go to the Enamine website, it's just enaminestore.com, search #real. You see that we have there's a chemical sketcher in there. And so you can just, so here I've just a piperidine ring and a phenol ring. You can basically, it's a typical sketcher embedded. And then just to show you the speed of the search, we can run it, and there automatically we have some hits from the real database. So you can also do this inside ICM, which we'll show in a minute. I think you can download these from their website into SDF format or other format, but you can also do this inside ICM and get a chemical spreadsheet and also analyze the data in a bit more detail, which we'll talk about. So at the back end of the GigaSearch, there's Molcart, and Molcart is a chemical storage cartridge which allows you to store large chemical compound libraries for searching and analysis. It uses a fast relational database which is freely available, MySQL, and the compound databases of any size can be stored in Molcart and analyzed and searched using ICM cheminformatics tools. There's a lot of sort of database administration tools embedded in it, such as managing databases, tables and users and privileges of it. And it obviously contains the fast chemical substructure and similarity search, and you can search using SMILES and SMARTS patterns, as well as fingerprint similarity and substructure combo. As we showed with the enamine, you can also embed. You can also have embed like a HTML editor to do the search. MolSoft has its own HTML5 molecular editor, which is freely available, which you can download from our website if you want to do that. But you obviously need the Molcart backend to do the actual search. So I'm just going to show some of you already have ICM downloaded and you have your license installed. So I'm going to show you how to do this searching in ICM. We're going to use an example, cyclooxygenase 2 inhibitors. They're quite a storied bunch of inhibitors. There's Vioxx and there's Celebrex. Vioxx was unfortunately removed from, well, it was removed from the market due to toxicity problems, and Celebrex has a black box warning. But the common trend of these molecules, they usually have like either a sulfonyl or a sulfonamide group and a phenyl ring here. So we're going to look through the real database of chemicals to find similar chemicals to these. So these are obviously involved in pain and inflammation relief. They are selective inhibitors, the members of the non-steroidal anti-inflammatory drugs, and they target COX-2, and which reduce the risk of peptide ulceration. So these are important drugs. And the main features, so there's Celebrex and Vioxx are probably the most famous, but there's lots of other COX-2 inhibitors out there. So we'll basically concentrate on this region here because it's one of the key factors which aid the binding of these drugs to COX-2. So practically in ICM, how would we do this? So we would have to, you should have an icon like this for ICM. You just load up ICM. And then at the top here, we have two buttons which look kind of similar. One has a pair of binoculars, which is for chemical search. This one is for chemical drawing. So the one we need to use today is the chemical search option here. So if you click on that option, you get this box to sketch in. And online there's other webinars on all our cheminformatics tools and how to use this, but I'll just quickly show you. So we're going to start with sulfonamide. So we can use the tools here. There's also embedded into the editor, there is a useful templates. If you've got a more difficult sketch to make, you could probably speed it up using the templates, or you can use the chemical dictionary here. We could actually type Vioxx and we can actually just load Vioxx, but I'm just going to sketch it here. Just going to sketch the sulfonamide group and then we'll go from there. So our aim in this example is to find similar chemicals in real that might be COX-2 inhibitors. So hopefully you can see this okay in the GoToMeeting, but this is our original query. So we sketched the query. We have this panel here, which is not much use. It's more useful for chemical sketching, but it sort of keeps an eye on properties as you sketch. I'm just going to remove that just for clarity. So we've made the sketch. Then we need to just going to go back here. So made the sketch. So it's asking us what's the query input. So in this case, it says draw, so we've drawn our query. You could actually input an SDF file and do multiple. You would see a panel of the chemicals here and do a screen of a large data set, but we're not going to do that in this case. It's asking us what our data source is. So if you don't have MolCarts, you may have chemical spreadsheets in ICM. So if you read an SDF file, it would be a table at the bottom here, and you would see it listed here. You may have an SDF file on your computer, so you could just search an SDF file. You may have MolCart, the chemical cartridge, with a number of different databases in there, so you could use that option. But for this example, for GigaSearch, we have online databases. And the one we have embedded, and you have as well, is the real database. It contains 1.1 billion chemicals. And so we're going to query that. Then there's different query options. So in this case, we're doing substructure search. But if you wanted to, for other files or other databases, you can also do similarity. You'll see different options. You'll see similarity and fingerprint similarity and other ways of searching. Then you can be more specific about how you want to match your query. So you can say, I want to match stereo, I want to ignore the salt, keep ring membership, and then also maximum number of hits is an option. You can reduce that or increase it. And then it asks you how you want to display your results. So one option would be to count the number of hits, or you can, if you had a chemical spreadsheet, you can select, so if you did the search, it will select the rows which match this search, which is sometimes useful. Then you can extract that to a new database. But most people use this save results to option. So it's saying, I want to save this to a new table called result, which is fine. It will, if you have a table called result, it will overwrite that current table. You can uncheck that option. You can also highlight the substructure match between, you'll see that in a bit, and we can store the query for speed. So we'll just click here, and so it's searching the real database. Okay, so when it's run, you'll get a table like this. So you can see that we have the sulfonamide group. These are the results that you will see. And you can see that for our COX-2 inhibitors, ideally we have like a terminal sulfonamide because it makes a nice hydrogen bond with an arginine in the cyclooxygenase pocket. But you will see that some of our hits we have connections here with the nitrogen and other groups, so that we would know that these ligands are not going to bind to our COX-2 inhibitors. So we would need to really refine our search a little bit more. At the moment, we're just doing a basic search. So we can refine our search here. If we click here and draw the sulfonamide. And we can add some more filters to our search. So, so we can say that we want this nitrogen to be as drawn, so that there's no connectivity to this nitrogen. So if you right-click on any atom in the search panel, you get some options. So if you, hopefully the right-click options show on GoToMeeting, I think they do. So you can see that we have different options here. And we want to say that we want this nitrogen to be as drawn. So we go to connectivity. So we could say we want this nitrogen to be connected to 2 other atoms, or 1, but we could just say as drawn here, shown here. So now you see we have a different, if I zoom in a bit, we have D1, which means as drawn, and the nitrogen at this point. So now if we do the search, we would obviously go back to online, the database, go to database real, and then you do the search, and then we get these kind of results. So you can see now we have, if we go through the list of our results, that all these sulfonamides are sort of terminal. There's no connection to this nitrogen at all in any of the hits. So we're slowly getting towards a decent, some decent chemicals that might have activity towards COX-2. But we can add some other parameters. So from looking at the other inhibitors, there's usually a phenyl ring here on this, or some six-membered ring in this position here. So we can right-click on this atom and say ring membership, so ring size, and say R6 for a 6-membered ring. So now you can, if I zoom in again, you can see we have this other filter here. So you right-click. So now if we run that option, so now we can see these are the results. Just for speed, I'm just running it. I'll have the results locally saved. So now we can see that connected to each of our sulfonamides, we have the ring, the nitrogen is not connected to anything, and go from there. So we're moving even closer towards Vioxx and Celebrex-like chemicals. And so the final parameter we could change is that if you remember back to that slide with Celebrex and Vioxx, Celebrex has a sulfonyl group and Vioxx has sulfonamide. So we can also make a change here in this at this point and say, we just zoom in, we can also add a condition here that this atom could either be a nitrogen for a sulfonamide or just put a carbon for a sulfonyl group. So to do that, we right-click on the atom and we choose the option element. So you could actually change the element here directly. You can also say any element at that point, but we want to be more specific, and you could say any aromatic, any aliphatic, or a variety of different options. But if you go to custom, we can modify this filter. So if we go to N, just put N, C, it's going to find sulfonamides and sulfonyl groups. Yeah. Just go OK. So now if we run the search, obviously the same thing, procedure, we get these results here. And so we can see the first hit, well, not, these aren't hits, they're just a search. So we have sulfonyls, sulfonamides, and lots of chemicals that look similar to our hits. So obviously you can extend this beyond these filters. You can add another bond here. Most of a lot of the high inhibitors, you can use a 5-membered, 6-member ring with a 5-membered, sometimes usually here, and we can add other searches. So if you right-click on any atom, you can see additional filters that you can add. So you can add, as with ring membership, it could be connected to, that atom could be connected to 2 rings, for example. You can define it there. Ring size we said R6, but you can change that to R5 or some other ring. You can say I want a charge at this point. Then hybridization state, aromaticity, connectivity. Sometimes it's useful to add an attachment point. So you can say I want an attachment. Definitely define an attachment at this point, and so you can just go here and take the attachment point, and you get an asterisk for the attachment point here, but we already have it for this carbon. So there's a variety of different options in the filters here that you can use to search Mockup, to search the real database. And you can also, in this panel here, although in the Enamine database there's no additional information such as molecular weight or number of hydrogen bond donors or acceptors, but if your database that you're searching has additional information, you can add additional conditions here, such as if there was a field called molecular weight, you'd see the option molecular weight, and you could say less than. This is a text. if there's a number, you see less than, and you can say less than 500 molecular weight, for example, and then add another condition, and log P or whatever information you have in your file. Okay. So the advantage of, just going to go back to my slides. So the advantage of running this search inside ICM is that embedded in ICM there's a lot of tools for post-search analysis. So obviously if you're searching a billion chemical database, you're going to get a lot of hits. And so you want a way of being able to filter those additionally. So in ICM, which I'll show you in a bit, you can also add properties to your molecules, as things like log P, molecular weight, polar surface area. We also have embedded some models that can be used so for ADME prediction, and also for things like HERG and KCO2 binding. Once you have properties in your table, then you can build fully interactive plots. So here we have log P against molecular weight. You can make selections here which are propagated to the table. And there's also an option to make multiple parameter optimization tools. So here we have these bars, which I think represent so these are, I'll show this in a bit. This is probably bars for Lipinski's rules, I think, but we'll show this example in a minute. Okay, so we have our final results, right? Shown here. These are some molecules which we think might be decent COX-2 inhibitors. So it'd be useful to add some properties to this table. So to add properties to a table, you go to the chemistry menu and you say calculate properties. And for this table, you can see that we have a number of different properties inbuilt for chemistry. So at the top we have most of the sort of Lipinski things, the log P, molecular weight. There's number of hydrogen bond acceptors and donors down here. You can flag groups in your chemicals that might be reactive. You can predict drug lightness. You can predict the pKa of the most acidic group and the most basic group. And then at the bottom of this table we have these Molescreen models. So in 2 weeks' time we're going to be discussing Molescreen models. There are Molescreen models for lots of different drug targets, as well as these sort of ADME tox targets. So we have prediction of KCO2, HERG, PAMPA binding, as well as prediction of half-life, and there's also a prediction of pains, which we can talk about another. If you go to some of our old screening webinars, it's an important thing to take into account whether your chemicals you're screening are predicted to be sort of pan binders. So these are the Molescreen models, but there's also like 2,000 other models which we'll show next in a couple of weeks' time for other drug targets. But these are embedded. So if you have ICM loaded, you'll see these options. These take a little bit longer to run because they're a bit more predictive models, but you can choose those options. But for this example, I'm just going to choose molecular weight, log P, polar surface area, and molecular area. So I just went to the chemistry menu, insert properties. So I'm going to add these properties to our table. Okay, so now we have these properties. So we can further filter our hits from the real database. One way to do that would be to build a plot. And you can build a plot in a number of different ways. One way is you go on the, so get these go-to meeting things in the way. So on the right-hand side here, we have the plot button, and you just click the plot button here, and you get a table, a dialog box asking you for different questions about the data that you want to plot. So for initially, I want to plot molecular weight versus log P here. So you just go OK, and that will build the plot, initial plot. Then I'd like to, you can add different dimensions to the plot. So I'm going to add, I want the plot points to be representative of the molecular area. We have bigger dots, and then color them by, so the options here, color by, and just choose polar surface area, and apply, and then we have these, the plots here. So these plots there's other options for, you can plot histograms and heat maps and other options as well. But there's, if you go to our webinar, other webinars, you can see those tools. So these are fully interactive. So if I wanted to select a subset of these chemicals, maybe log P region 2 to 3 and a molecular weight of 450, maybe these. You can see these are selected, and this selection is propagated to the table. So we can actually make a new table, or a new database, by just right-clicking here and say copy rows to a new table, and that will extract those hits, and you can rename the table as you wish. So that's one way of analyzing the data. Okay, and another way would be to cluster your data. So there's the clustering, all the tools related to the table, the one I use for plotting and everything, are here in this panel here. So the one for clustering is this button. So if you click on that button, it asks you there's a number of different clustering methods embedded in ICM. But the one we're going to use to cluster this table is the molecular fingerprints of these chemicals. So we click on the mole column. The mole column is the column containing the 2D structure, so that's the one to select. You can also cluster by other columns if you're doing other things. If you have other numerical data, you can cluster by anything basically. But in this example, we're clustering by fingerprints. And these are the different methods we have embedded. But we'll just use the default clustering method. If you go OK, then you'll see a clustering tree on the right-hand side, and the table is clustered by the branch that it's in. So you can drag the distance bar here, depending on how close you want to, how you want to differentiate it, the tree. So these are, if you drag it, you're going to get more and more branches shown here. So there are a number of different tools in the clustering algorithm that you can use to make selections. One of them usually is quite useful is select centers. So you can just click select centers, and that will select a representative center from each branch of your tree. So you can see selection here, it's propagated here. And then once again, you could just take that and choose copy to table new, and you can build another database, another more diverse set for synthesis or for testing. another useful option in here. Sometimes in your table you may have, for example, a docking score or some other parameter that you want to prioritize. So you can say select centers by, and you can choose by, and then say by minimum molecular weight. Might not be much use, but if there was a score here, you could say by minimum score. If the lower the score, the better. Then it would select based on score rather than just a representative center. And there are also options for, if you've got a very large cluster, it will select more from the bigger sets based on this, or you could just choose one from each one from each cluster. Okay, so these are all ways to analyze your search results. And finally, you just want to end up with the multiple parameter optimization. So you may have like 20,000, 30,000 hits here. Just for this example, it's going to take a very small set and copy that to a new table. Just for speed, have a little set here, and I want to then use what's called multi-parameter optimization. So if you go to the chemistry menu, go to MPO here, there's an option to create new MPO score. So go chemistry, MPO, create new MPO score. So now you get this panel, and there's different scores that you can build. So you can give each chemical a score of how well it fits into the Lipinski's rules. For CNS, how well your chemical is likely to cross the blood-brain barrier or not. This is QED is another drug-like prediction method by Pfizer, and there's a paper, you can see that. I can send that to you if you're interested in reading more. And there's also empty, which means you can set up your own score. So if we look at one of these, so let's look at Lipinski. Let's go OK. So for this Lipinski score, by default we have the main properties that define Lipinski's rules. So log P, molecular weight, number of hydrogen bond donors, number of hydrogen bond acceptors. This is all going to be calculated on the fly and given a score based on these parameters here, which you can play around. It's kind of a separate webinar, but you can play around with the weighting and the shape of this slope. We can show that another time. So then you just basically go calculate MPO score, and we should see a score column. Now for each of our, I'm going to get rid of it. Drag this over here. So we have a score here for how drug-like our, you can see the log P going up and down as we browse through this table. And so you can sort by the MPO score if you want to. So the higher the score, the better this fits into drug-like parameters. So if we go to the bottom of the table, we'll see the number of, for example, number of hydrogen bond acceptors drops off here, log P, whatever. As we scroll up, we can see the score, log P changing. So yeah, this is a useful tool for analysis of the data. So if we just quickly look at the other options there. So if you go to CNS, you can see we have, for a CNS model, we also have we have polar surface area prediction incorporated into the score, into the MPO, as well as the pKa of the most basic group. If we go to the other inbuilt, these are inbuilt ones, go to QED, so this is the quantitative estimate of drug likeness, and it's there's a paper here which you can send to you, or you can look it up here. So these have a bit more advanced. Maybe Eugene can explain it in the questions, but you can play around with how these shapes are biased. But this is based on that paper about the best weighting for each of these different properties. So it has additional ones compared to the Lipinskis. It's got number of rotatable bonds, polar surface area, aromatic rings, and other things. And there's an empty one, as I mentioned, where you can define your own parameters based on the data you have in your table. So I just want to thank you again for your attention and if you're interested in the webinars. Please get in contact with me by email if you have any questions. We'll try and answer some that have come up during the webinar today.